Let's try and calculate this thing. Okay, using the residue theorem that we've learned. Okay, now when I said at the start of the course that one of the really striking and exciting things for 18th, 19th century mathematicians was that this complex world allows us to answer questions in the real world, what we can't answer, or they couldn't answer beforehand. In fact, still can't answer without these techniques. And that's really strange. That was really striking because the real world doesn't contain complex numbers, but we learn things about the actual world of real quantities from doing things in the complex plane, from this theorem of the residue theorem. This is not an example. This guy we can calculate. Yeah, we can calculate. How would we calculate this if we were doing calculus, if this was a calculus exercise? Yeah, the antiderivative of 1 over 1 plus x squared is arctangent. This thing we can actually calculate. Yeah, so we actually know the answer to this guy. It's not a hard one. Yeah, but we're going to get the answer from a completely different source. We're going to get the answer from the residue theorem. Yeah? So if we want to do this from the residue theorem, then we're going to have to think about this as a contour integral, or part of a contour integral. So we're going to do the following thing. Or maybe not think of this, or transform this, or think of transforming this into a contour integral. Contour integrals over, well, we've learnt them over nice curves, right? So we don't want to do anything from 0 to infinity. We're going to do something from minus r to r as r gets bigger. And we're going to create a contour like this. So we're going to have minus r to r, and we're going to create a semicircle like this. Okay? That's the contour we're going to do, and that's called gamma of r. Yeah? So I hope gamma of r is clear, and I don't have to explicitly define it. It's just this semicircle centered on 0. Yeah? So consider the contour integral gamma of r 1 over 1 plus z squared dz. Now, the part which is along the base of this guy here, this part is exactly part of the thing we want to understand, because when z is on the real numbers, then 1 over 1 plus z squared is 1 over 1 plus x squared. Yeah, that's exactly what we want. Yeah, so this is the thing we're actually interested in. Yeah, and it turns out that we don't have to care about the other part, particularly because if we look at the other part, so let's call this other part here. Well, actually, let's not bother. Let's just use the notation we have. So this thing can be broken down into the integral from minus r to r of 1 over 1 plus z squared dz plus the integral of the other part. The contour take away that part. And I claim that thing here we don't have to care about, because as r gets bigger and bigger, this thing will just vanish. And let's see why. So if we just create a parameterization, so let z of t be a parameterization of this part right here. So let's let it be r e to the it, where t goes from 0 up to pi. Then that's exactly this, giving this guy right here. So z prime of t is equal to I r to e to the it. So then this thing in the red box turns out to be integral from 0 to pi of 1 over 1 plus r squared e to the 2it, like this. And then the derivative, let's put it here, I r e to the it dt, right? So we can take the absolute value signs, right? And then this thing is less than the length of this thing. Well, now it's just an ordinary integral, so it's less than pi. And then let's put the absolute, actually let's do it since it's just now an ordinary integral. That's the integral from 0 to pi, and then we put the absolute value signs throughout this. So the absolute value signs, if we put the absolute value on the top, we just get r, right? If we put the absolute value on the bottom, then this expression here, as we arrange t from 0 to pi, it's always going to be less than 1 plus r squared. Because this is 1 plus a complex number. So this is the number 1, and then plus a complex number. Yeah, and the very worst thing it can be is if it's on the other side, right? So it can be here, it can be here, right? I mean, this is not a big point, because the 1 is insignificant compared to the r squared. But it nevertheless is the truth that we have this inequality. We just see from this geometry. Yeah, this is dt. So that's just equal to pi r over 1 plus r squared, and then this goes to 0 as r goes to infinity. So as r goes to infinity, we don't have to care about this part right here. So it does become just the integral over the base of this guy here. Yeah? Yeah? Okay, and what's cool is that this is now just an integral of a function over a closed curve. And it would be 0 unless we had some singularities inside the closed curve. So what do we see happening here? What singularities do we have going on here? Not quite. So let's try and factor z squared plus 1. How can we factor it? It's a complex polynomial, so we can definitely factor it. That's what we learned. So what are the factors? What are the factors? Yeah. Z minus I, Z plus I. Yeah? Cool. All right. So then this thing becomes this guy. Z minus I, Z plus I, dz. Okay, so what are the singularities inside our contour? I, yeah, sorry, I thought you said pi, yeah. I. So this is our only singularity inside our contour. The other one is on the other side, it's outside, yeah? Cool. All right, what is the nature of the singularity? What kind of singularity do we have? You might be muted, Annie. Unmute yourself. A pole. What kind of pole? A simple pole, yeah? It's a simple pole, yeah? Its blow up around I is just of order 1, right? Yeah? It's actually already in the form of 1 over z minus the point of the singularity times a holomorphic function. And this is nice holomorphic around the value I itself, yeah? So we have a simple pole at this thing, yeah? So what we need to do is just write 2 pi I, and then the residue at I of this function, let's write it like this, 1 over 1 plus z squared. That's the residue theorem. That's what it tells us. Yeah? There's only one thing, and the residue is easy to calculate. Well, the residue is easy to calculate because it's just a pole. The residue of this guy is the limit as z goes to I of z minus I of this function. And we write the function as z minus I, z plus I. And then these minus i's cancel, z minus i's cancel. So this is just the limit as z goes to I of just 1 over z plus I, which is just 1 over 2i, which is just minus I over 2. Yeah? Cool. So from this thing here, from star, we have that the answer should be 2 pi I times minus I over 2. So what's that? Minus I times I is just 1, so that's just equal to pi. So we think that for every single r, the integral of this, where is it? Where is my guy? Of this function is just equal to pi. That's what we think. Huh? Yeah? Cool. So how do we conclude the proof? Well, this is true for every single r. So we can take the limit as r goes to infinity. So pi is equal to the limit as r goes to infinity of the integral around gamma of r, 1 over 1 plus z squared dz. Yeah? And in the limit, when we break it up like this, then this part survives and this part vanishes. So this thing just turns out to be the integral from minus infinity to infinity of 1 over 1 plus x squared dx, which gives us the answer. Now let's see what calculus tells us. Let's see if mathematics is consistent. So let's do it right there. So this is an even function, so it's like this. So this is 2 times the limit as r goes to infinity. The antiderivative, as you people told me, is arctan. And sure enough, we know what arctan looks like, right? It looks like this. Horizontal asymptote at pi over 2 and minus pi over 2. So this thing is just 2 times pi over 2, which is just pi. And that is the right answer. Yeah? In this particular case, it's actually easier to use calculus than it is to use the residue formula. Huh? But this is just the beginning, because this now has enormous power. Now we have the ability to transform real integrals into contour integrals in some way, like such as this, taking the limit. And in all cases, we're going to do something like this. We'll have some contour where we expand it in some way so that the only parts we're interested in are just the real parts. And then we'll be able to extract out specific things, exact answers to real integrals that are inaccessible from real analysis techniques, yeah? Which is absolutely extraordinary. So entering the complex world, proving these deep theorems about things in the complex world, things that don't exist in the real world, gives us information about the real world. Yeah? Yeah? This is a completely different way to calculate this quantity. This is completely different. Yeah? These are in different parallel universes, these two answers. Yeah? But we get the same answer. This stuff does give us this kind of thing. So yeah, imagine excitement back in the 18th, 19th century when they started to see this and realized they've been struggling for hundreds of years to explicitly calculate various integrals. And then this bunch of techniques comes along, and suddenly you can do it by just calculating the residue at various singularities of holomorphic functions that have poles at certain points inside contours. This was very hot stuff, cutting edge stuff, and it's still very hot stuff. It's still very, not in the sense of cutting edge stuff, but it's very neat. It's very impressive. It's very cute. And yeah, that's what we're going to be learning in the next class. We're going to practice this on other integrals.